Okay, let's get started. In this lecture, we're going to take a look at linear functions. Now, having defined what a function is, looked at a few examples of functions in the previous section. Let's take a look at just linear functions. That's all we are interested in this section. So first, we're going to define the most general form of a linear function. The linear functions that we are interested in will have the form f of x equal ax plus b, where a and b here are real numbers. And if a is 0, of course, this part is 0, so you get a constant function f of x equals b. Okay? But a and b here are elements of the set of real numbers. All right. Now, these functions, if a is different from 0, has domain and range, that's all real numbers. And if a is equal to 0, again, we get a constant function whose domain is all real numbers, but range is just the number itself. So this is what I'm thinking. Suppose I have a constant function like that. This is f of x equals b. Remember, a is 0 here. This is point b. And here's x. I'm assuming b is positive. Again, positive, negative doesn't matter for the argument we are making. So here's the function. Notice domain is our real number. So the funny looking d here, that means domain. Now let me draw it better now. There you go. Domain of the function is going to be all real numbers. And in this case, the range of this function, r of f, is simply going to be a number, right? It's always b. Therefore, the range is just going to be a single number. So that's going to be just b. That's the case where a is 0. And if a is not 0, of course, then domain are real numbers, ranges are real numbers also. Now, let's take a look at, for example, let's do a graph of this one right off the bat so we see how this works. Now, when we graph these linear functions, again, we're going to graph them initially by plotting points until we talk about different variation in forms of a line. But in this form where you have f of x or y equals a function of x, then we can plot points. For example, remember y and f of x are the same thing at this point for us. And I can let x be 0, another I'm going to let the function be 0. So what I'm thinking is I want to plot the intercepts is what I'm doing. So when x is 0, you put 0 here for x. We get 0 times negative 2 is 0 plus 6 is 6. And when I set the value of the function equal to 0, that's like setting negative 2x plus 6 equals 0. And we can solve for x. X ends up being 3, right? There you go. Now the fact that in one y is 0, in the other x is 0, that means I'm plotting the intercepts. 0, 6, place where x is 0, this would be the y-intercept. And 3, 0, place where y is 0, that would be the x-intercept. So I'm plotting the intercepts for this line. Okay, and to do that, let me get my coordinates. I'm gonna grab my shapes here. I'm gonna grab this one, and let me just, that will help me graph these a little better. Right? And there you go. So there's my coordinate system. Now in this coordinate system, of course, the horizontal is x, the vertical is y, and 0 is the origin. So 0, 6, I'm going to call this to be 6. And there you go. That would be 6. And 3, 0, that would be almost here, but x is 3, y is 0. And let me move my y to the other side because I'm about to draw a line here. Okay, so this line that we're going to draw is going to be, let me get my ruler here, and the ruler I'm gonna, because I just want to make sure I'm drawing this in a straight line fashion. And let's see if I can. There you go. I knew I could do it. So there you go. That's my ruler. And there's my line. Perfect. So there we have it. Okay. And so there's a line. That's the graph of that line, drawn very nicely. I'm proud of myself. There you go. So I've got the 2 points here. I got the point 3 and the other point is 6. Remember again, these are the intercepts. 3 comma 0, this would be my x-intercept, and 0 6, that would be my y-intercept. These are the points where the line crosses the x and the y axes. And commonly this is what we would like to draw. So there you have the graph of this function. Let's take a look at another function. For this function, I'm going to make up a constant function. What if I have f of x is equal to -4 now? Well, notice here the ax is 0, which means a is 0 in the general form. This is where a is 0. So to graph this one, suppose this is my, there you go. Here's my coordinate system, x, y. And -4 is this point. And I guess I could go a different color on the function itself. There, let's go there. And there you go. That would be the graph of this function, the constant function. Notice again the domain of this function is all real numbers. But its range, R subscript f means range of f, it's just a single number, -4. The one I did earlier, the one above, its domain was all real numbers, and its range was all real numbers also. All right, so there we have a couple of examples of these. Now, the standard form, by the way, of these equations that lead to a line, so I'm just going to say standard form of equation of a line. Let me write that, standard form that we're going to be using is in the form ax plus by. Notice x and y are both on the same side. The ABCs are numbers. The x and y are independent, dependent variables accordingly. So let's take a look at now, for instance, suppose I want to graph this equation 4x -5y equals 0. And again, what I like to do is I like to plot points here. So notice I'm not using the function notation. So I'm going to let x be 0. When x is 0, 0 -5y is 0, so y must be 0. Okay. Now, anytime when x is 0, y is 0, and vice versa, you choose y be 0, x becomes 0. That means the line will go through the origin. So it will only have one intercept, remember? And there you go. So that would be the equation of this line, and that's of course the graph of that equation. Now, I need one more point just so you see how I drew that slant line. So for example, I can let, I don't know, x to be 5, or better yet, let me do this. If I solve for y in that equation, -5y equal -4x, and divide both sides by -5, so I get y is equal to 4/5 x right in here. So if I let x be 5, 4/5 of 5, 4/5 times 5 would be just 4. So here's a point where, for instance, this is 5 and this would be 4 right here. So I get my 2 points that way, and then draw through the 2 points. This point is 5, 4. And that's how you can draw the line. So notice where 0, 0 is the y-intercept, the line will go through the origin. Okay, so let me write that. If C in general, in the general standard form, if C is 0, then the line will pass through the origin. That is the origin of the coordinate system, of course, as 0, 0 by that. There you go, 0, 0. And there we have it. The other thing, by the way, since we're graphing, plotting points, and we're doing the intervals, both of these, we use intervals, right? We use interval for interval notation, and we use like parentheses to plot points. So just got to be careful with when we talk about domain range, the intervals, parentheses indicate the intervals, but when we do points, they represent the coordinates of a point, the parentheses, not an interval. So just got to pay attention to that detail. Okay, so there we have this one. Now, if you look at, for example, this line that I have drawn, and also the one that we just did, both of these, the lines, this one and the one I just did, both of those have some kind of a slant to them, right? So I guess it's appropriate to talk about the slope of a line at this point. So when we talk about the slope of a line, we're talking about the measure of, as I mentioned, slant, or some say the steepness of the line. Steepness, and in addition to that, let's throw in orientation of that line. And what do I mean by orientation of a line is whether the line is going like that or whether it's going like this. That's its orientation, right? How it's going to be oriented, located. When we talk about the slant and steepness, usually we talk about a number. We try to quantify, and that's how we quantify how steep a line is, putting the number to it, and that's what slope is. So let's kind of create this notation for a slope. Now, slope of a line, the common letter that's used to represent slope instead of writing it is M in most algebra textbooks. And the slope of a line, to measure the slant or steepness, we need to look at the change in y over the change in x. That's your familiar rise over run, correct? And what is this rise and run, or change in y over change in x? We're talking about the change as we go from one point to another. So I'm going from point P, let's say, to point Q. Okay, and that's what we're looking at. How far did I change in the y direction as opposed to change in x? Okay, so this would be, in this case, the rise, and this one would be the run between any 2 points on the line. Okay, now this change in y, we're going to use a new notation you may not have seen. We're going to use this triangle notation, which is really Greek lettered for delta, and that's going to be delta y over delta x, and that's given by y2 minus y1 over x2 minus x1. Again, those represent the change in the vertical direction, the denominator change in the horizontal direction. And the notation here, again, I mentioned it, that's Greek delta. There are two deltas in Greek alphabet. This is delta, the other delta looks like that, which is used quite often in calculus courses. And so you will definitely see both of these notations in your calculus classes as well. Now, let's see, y2 minus y1 over x2 minus x1. Now, because this is a fraction, by the way, we can also write this as y1 minus y2 over x1 minus x2. Makes no difference. Indeed, just to show you, if I factor a negative from this fraction, factor from the top, factor from the bottom, this becomes y2 minus y1. Factor a negative from the bottom, it becomes x2 minus x1. Negative over negative is positive, and you can see that you get exactly what's up there. So it really doesn't make a difference whether we go y1 minus y2 x1 minus x2 as opposed to the other one. Now here's one thing I could not do. I cannot go y1 minus y2 over x2 minus x1. This one is a no-no. So they have to flow in the same direction in terms of the subscript goes. Either both of them go from 1 to 2, or they go from 2 to 1. Okay, top and the bottom both. We cannot mix and match them. And there you go. So that is really what the slope of a line is. Now, one thing to note here, by the way, let's make actually a couple of notes here. One is for the vertical, the other for horizontal lines. So for vertical lines have no slope. In other words, this concept of slope is undefined. It is not defined for vertical lines. And the reason it is not is this. Suppose I have a line here, and I'm going to go from one point to another point. Doesn't matter. Let's say I'm going from P to Q in this case. Okay, going from P to Q. From P to Q. I'm going too fast here, getting ahead of myself. All right, now, so as I go from P to Q, notice in a vertical direction, and suppose the coordinates are x1, y1, x2, y2. Now notice as we go from top to bottom, there is no change in x, but there is a change in y, true? So if I look at the slope as the change in y over change in x, then we said that there is a change in y. So there is a delta y, whatever that might be, the number doesn't matter. But there is no change in x. The delta x is 0 in a vertical direction. Division by 0 is undefined, therefore this concept is not defined for vertical lines. What if we have horizontal lines? For horizontal lines, we will look at horizontal lines. The slope, again, let's go ratio of delta y over delta x. And here's an example now. Suppose I have a horizontal line. Here's point P, and here's point Q. Now, as I move from P to Q, Q to P doesn't matter again. But you can see that there is a change in x, right? In the earlier one, there was a change in y, but no change in x. This one has a delta x. That means there is a change in x. But there is no change in y, right? Delta y is 0. Up here, delta x was 0. So if delta y is 0, I have 0 over delta x, which is non-zero, right? That number is not 0. There's actually a distance. So this would be 0. 0 divided by any non-zero number is 0. Therefore, for all horizontal lines, the slope of the line will be 0. Okay, so we have those two notes to make. Now, let's generalize now for y equal ax plus b in general. If the line is written in what we call the slope-intercept form of a line, or let's say general form in this form for now, we can define m, again like before, to be a delta y over delta x. Okay, delta y is a change in y. y2 minus y1 over change in x, which is x2 minus x1. Now, for this y2, now using function notation, y2 would be f at x2, y1 would be f at x1 over x2 minus x1. So that's what the slope is. True? Now let's actually plug in f at x2. Again, remember y and f of x are the same thing for what we're doing. So I'm plugging in x sub 2 into the general form. So it's going to be ax sub 2 plus b. And then we're going to subtract ax sub 1 plus b from it. Then we're going to divide by x2 minus x1. Now we can distribute, remove parentheses. The first set of parentheses, just erase them, nothing changes. When we remove parentheses in the second expression, second binomial, you have to distribute the negative sign over to both terms, right? There you go. We got to distribute them to both. So both of those terms become negative and divided by x2 minus x1. So we do have a couple of opposites. And then in the numerator, I can factor the a, that becomes x2 minus x1, divided by x2 minus x sub 1. Okay, and now we have a common binomial factor, which we can divide out. And long story, we managed to find the slope for the general form m is a. So in the form ax plus b that we have up here, a represents the slope we just showed, represents the slope of the line. So if I have an equation, let's say y, for example, let's say we have, let's make this one. Let's say an example here. Suppose I have f of x is equal to 2/3 x plus 5. So based on what we just said, the coefficient on x, the number that multiplies by x, is equal to the slope. So I can simply say slope is 2/3 x without graphing or showing any work, as long as we can recognize the standard form. All right. Now, the last idea of this section is we're going to talk about the average rate of change. Remember, in mathematics, a rate is actually a fraction whose numerator denominators have different quantities. So that's what the rate is. For example, how fast you drive. You go at a rate of, let's say, 60 miles per hour. So you have a fraction whose numerator is one quantity and denominator is a different quantity. So it's the ratio of two quantities that measure different numbers. Or for example, let's say, I don't know, you're buying eggs. Okay, eggs are precious commodities now, so I'm going to go $6 per dozen as of the making of this video. Okay, and there you go. So that is a rate. Now we're looking at a rate of change, and specifically we're looking at the average rate of change. So for average rate of change, let me do my do a graph first. There is our coordinate system. So here is 0 in here, and suppose I just draw this general curve. Now if I draw a secant line is a line that connects any 2 points on the graph of an equation. So this is what we call a secant line, joining 2 points on the graph of this equation. Now the points here, suppose this point is A, and this point has x that is B, and thus this would be f at A, the y value, and here I have f at B, the y value for the second point. All right, so we have, that's the geometry of what we're about to do. Now, if I look at the change as I go from point P to point Q, from lower to higher. Now, low to high, high to low doesn't matter. The formula will adjust itself according to the coordinates. So suppose I go from lower to higher point. Well, this would be the change in x, right? That would be my delta x. In other words, I would go over this way and then I go up, right, to get there. So that would be my delta y. And this is delta x. All right. Now, remember the slope of the secant line in this case. The slope is going to be delta y over delta x. All right. And that change from P to Q, this is what the average rate of change of the function is, going from A to B. So the average rate of change of the function on the closed interval from A to B, therefore, is going to become f at B, the higher point, minus f at A, the lower point. That's what delta y is. The higher point minus the lower point. Right? It would be this distance. And delta x is simply b minus a. And that is what we call the average rate of change of a function. Now this idea of the average change becomes more paramount as we go to calculus, because in calculus we actually differentiate between the rate of changes. We have two types of rate of change. One is the one we're working with. This is the average rate of change. So at low point is this, at high point is that. So the average rate of change doesn't look at what happens in between. So for example, if I have a function here at a goes high, low, high, low, high, low, high, like that, and this would be, let's say, point B. It only looks at 2 points, the starting point, the initial point, and the terminal point. It looks at the change of the function. You see that? Delta y, delta x. It just looks at 2 points. It ignores everything that happened, how the function behaved at different time intervals, or they're just simply different intervals. So we have two kinds of rate of changes then. We have the average, which is the one we're doing in this course, in the college algebra. And then, of course, in calculus, we have the instantaneous rate of change. That would be the change of the function at an instant of time. All right, so you'll get to that eventually, and we'll be talking about those kinds of changes later on in a different course. But for now, just the average rate of change. So let's take a look at now some examples. Okay, in my first example, I'm gonna take a look at, let's say we want to graph a function in our example. So suppose I want to graph again negative 4x plus 3y, this time equal to 12. I did one where it was 0, but suppose this time this one is 12. So remember, we would like to plot easy points. All we need is 2 points, and we're going to pick smart points. So I'm going to let x be 0. When x is 0, this portion of this equation is 0. I can easily solve for y. 3y 12, so y must be 4. And there we have that one. And then the other part, when y is 0. For this one, when y is 0, 3y is 0, that term disappears. I can solve for x. Divide both sides by negative 4, and we get negative 3. All right. And now we have our ordered pairs that we need. 0, 4 is one, and negative 3, 0 is the other one, right? Again, place where x is 0, that's going to be the y-intercept. Place where y is 0, that would be the x-intercept. So I'm plotting the intercepts in this case. Okay, and just to make it simple and easy, suppose I have it like this. 0, 4 would be this point, and negative 3, 0, let's say, is this point, and negative 3. There's x, and here's y. And all I got to do is just connect the dots together. And when I do, I get the graph of this equation. So there's a linear equation, and there's the graph of it. Okay, and that's all we got to do. Now, when you graph, please make sure you label your coordinates, the x and the y. If you don't, it just doesn't look as good. And we try to label. Labeling is putting the numbers on the coordinate system. We try to label the key points, especially if there are intercepts. We want to label the key points. Let's take a look at another example. One that I haven't done is this one. What if I have something like x equals 3 now? Okay, notice for this one, if I think in terms of the standard form ax plus by equals c. So I have x equals 3, so that means by is 0, correct? Well, how can by be 0? Divide by b, that's when, well, actually, no, I don't want to solve for y. But the only way, because y is allowed to be anything, the only time by can be 0 is if b is 0. If we are allowed to choose different values for y. So for instance, if y is 5, b times 5 is 0, so b has to be 0. So that's what I mean. For if you allow y to be whatever it wants to be, then b has to be 0 for that term to be always 0. So, make a long story short, I can write it as 0y. Okay, the missing term, I can write it with a coefficient of 0. Now, if I plot points, let's say when x is 0, remember, there is no y, and that's not possible, right? So undefined. x cannot be 0. Well, it turned out the only time x gives you a true statement, true equation, is when x is 3. When x is 3, y is 3. In fact, x is always 3. Y could be anything, right? Look at this one. 0y equal 3. I'm going to let y be 100. Something we usually don't. And x would be 3. See that? Y is 100, x is 3. This was not acceptable. Point 0 undefined. So let y be -2. X again would be 3. So it seems like x is always 3 regardless of the y values. So if I draw this thing, then here's 3, and y could be anything, right? Positive or negative. Therefore, the graph of this is going to be a vertical line at 3. Okay. And I'm going to write that one. The graph of x equal to a constant and I'm going to call it k. So x equal k is a vertical line at k. K could be positive, negative. K is a real number. And the graph of y equal to a constant, we would expect that one to become a horizontal line, right? Okay, so I can write that now. We're going to put the graph of y equal to k, a constant. This would be a horizontal line at k. Remember, horizontal lines, this one is a function, constant function. But the vertical line, this is not a function, just so you know, not a function. So I cannot say, I cannot use the function notation for that one. All right, and there is the graph of this one. Now, next, let's say I want to find, we talked about the slope. So let's say I want to find the slope of a line through 2 points. Example here, let's say I want to find slope. Okay. And the points are, let's say I use P and Q, so 0.58, and Q is going to be another 0.312. Again, the slope is going to be a change in y, y2, y1, x2, x1. Now the points themselves don't care what we call them, so I can go x1, x2, or I can go x2, x1. As long as we remain consistent, see, with that notation, that's y1, y2. The one below it, these are y1, y2. So it doesn't make a difference. So I'm going to go ahead and go with the lower ones. The slope's going to be y2, that's 12, minus y1 is 8, divided by x2, that is 3, minus x1 is 5. 12 minus 8 is 4, 3 minus 5 is -2, 4 by -2 is -2, therefore the slope of this line is -2. Okay. Now, let's say now I want to find the equation of a line. Okay, suppose I want to find, or actually not the equation, we'll get to that later, but I still want to find the slope. Suppose I want to find the slope of a horizontal, hint, hint, horizontal line. And this time I want it to go through 5, 1. Okay, so if I plot the point, okay, 5, 1, well, 1, 2, 3, 4, 5, 1. Suppose this is 5, 1, and I want it to be a horizontal line, right? That's the key. A horizontal line through 5, 1. Okay, so what is the slope? Define slope. The fact that this is a horizontal line, remember the function would be f of x equals 1. The y value here is 1. But the slope doesn't matter how high or low the line is drawn. As long as it's horizontal, slope's going to be 0. And that's what we wanted to find, the slope of the line. That's it. What if I have a vertical line? Another example. So let's say I want to find the slope of a vertical line. This time through just doesn't matter, some random point, let's say 4, -7. What would that be? The fact that this vertical line, I don't even need to graph this thing. Slope is going to be undefined because it's a vertical line. Doesn't matter what the point is exactly, could be any point. So that one, the answer is undefined. And let's see what else we did. Let's say in another example, this time I want to graph the line. Okay, let's say we want to graph the line, and I want to graph the line that passes through. Let's say it's going to go through a point, make that 3, -4, and suppose we wanted to have a slope -1/3. Let's say how we're going to graph this line. Okay, so to graph this one, first I need to identify the point, right? Here's x, there is y. The point is 3, -4. So 3, -4, 1, 2, 3, and -4. Let's go 1, 2, 3, -4. So this is the point that it's going to go through. We want it to have a negative slope, right? Here's 3, -4. Now, because the slope's -1/3, I can always write -1/3 as such, right? All three of these fractions, all three are -1/3. I want to go with this option. I like to keep my run positive, my rise positive, negative doesn't matter, but I like to keep my run always positive. And here I'm going to think about in terms of change in y over change in x as rise over run. So as from this point that we are at this point right here, the rise is -1. So for a rise of -1, you actually go down 1. True? Down 1. And then the run is +3. So I'm going to go 1, 2, 3 to the right. This would be my next point, wouldn't it? So the fact that the rise is negative means I'm now at -5. And the run is +3. So I go from 3 over 3 more. So now I'm at 6. The coordinates of this point, therefore, are x, y. So I went from 3, -4 to 6, -5. And we can draw this line now. And there you go. That would be the graph of that line. You see that? So I use rise over run as I go from higher point to, it just so happens that's the lower point. Now, it actually makes no difference how we select these points as far as rise and run goes. Some other people may do this way. They go with this option. Let me go with that option, 1 over -3. This time the rise is positive, and the run, if it's negative, less than 0, means you go left. So let's see. From this point, I rise 1 and run 3 positive. So when I go up, up, and over. So there you go. So I end up with a different point, right? I end up on the higher point. And once you connect the dots, again, you get the exact same number here. And actually, not same number, I'm sorry. I mean, you get the exact same line when you graph the line. So however you graph it, that's the graph of this line. Okay. And I think that's probably all we wanted to talk about. Let me do one more where slope's positive. So this time I wanted to go through 2, 4 and slope to be, I don't know, positive 1/2. All right, so how are we going to do this one? I'm going to go through point 2, 4, 1, 2, 1, 2, 3, 4. We want to go through this point, and the slope is 1/2. So again, rise positive, run is positive 2. A positive rise, so we're going to go up 1 and over 2 to the right. This would be the next point, and that would be the graph of this line. If I want to label the points, I went from 2, 4, up 1. So you go from 4 to 5 now, that's the rise. And the run was 2, so I went over 2, from 2 to 4. There you go. So the coordinates of this other point is going to be 4, 5. And there you have the graph of this line meeting the conditions. All right, and that is all we're going to talk about in this section. Again, thank you for watching the video, and hope everything was clear, that I was able to explain things relatively easily for you. Thank you.